Hi, everybody. Now we're going to introduce an invariant of permutations called their sign or their parity. We're going to be able to divide up permutations into two classes, even permutations and odd permutations. And this gives us some very basic insight into the structure of the group of permutations, the symmetric group on n elements. The key building block in this study are going to be the simplest non-trivial permutations, which are called transpositions, which are permutations which just interchange two of the numbers from 1 to n and leave everything else alone. And in some sense, you can use the transpositions to build up all of the permutations. So let's look at this a little more closely. So first we have a definition, and we introduce the idea of a transposition. A transposition is a cycle of length 2. So an example of a transposition is the cycle 2, 3. This is the permutation which takes 3 to 2 and 2 to 3 and leaves everything else alone. And in some sense, I guess you can say that the transpositions generate all of the permutations. That is to say, if all you had were transpositions, if all you could do was flip two elements, interchange them, that would still be enough if you wanted to, let's say, rearrange a list. And all you were allowed to do was each step would be to flip two of the elements in the list. That would be enough to rearrange the list into any order. And that's what the meaning of this proposition is, that every permutation can be written as a product of transpositions. Not in a unique way. I mean, there may be lots of different ways to do this, but there's always at least one way. And just as a remark, you might ask, well, what about the identity element? And so by sort of tradition or convention, we should think of the identity element as the product of no transpositions at all. It's the product of 0 transpositions. So every non-identity element in the symmetric group is a product of at least one transposition. And to prove this, we can use the fact that every sigma in the symmetric group is a product of disjoint cycles. We proved that before. So if we have our sigma as, let's say, R1, R2, out to Rk, where each Ri is a cycle, and then we can write each cycle as a product of transpositions, then we put all that together and we've written our sigma as a product of transpositions. So it's enough to show that every cycle is a product of transpositions. And this we can just write down. So suppose we have the cycle A1, A2, dot, 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 up to AN. So remember, this is the permutation which sends A1 to A2, A2 to A3, and so forth, and finally takes you to AN, and then back to A1. And I'm just going to show you how to write that as a product of transpositions. You take the first, you interchange the first and the last, and then the first and the second to the last, and then the first and the third to the last, and so on, all the way down to the first and second elements. And I claim that this product of transpositions gives you the cycle. And for that, we can just check. So let's multiply these transpositions together. So first we have, let's start with A1. So we have A1 goes to A2, and then if you look back through this whole list, you see that A2 never appears again. So once A1 has gone to A2, it stays there. Now we take A2. Well, A2 goes to A1, and then A1 goes to A3, and once you get to A3, A3 never appears again down this whole earlier list, and so A2 ends up at A3. And now you could take A3. Well, A3 goes to A1 by this transposition, and then A1 goes to A4, and A4 never appears in an earlier list, and so on. And finally, you get to AN minus 1. AN minus 1 here goes to A1, and then A1 goes to AN. So you have AN minus 1 goes to AN. And then when you finally work out AN isn't in any of these. So AN gets left alone by all of these, and finally AN goes to A1, and that closes the cycle. So if you were sort of thinking about what you're doing here, you're taking if you want to sort of think about that in terms of the cycle, starting at the right, you interchange A1 and A2, then you interchange A1 and A3, which is really A2, and you work your way back, and what you end up doing is rearranging the cycle back to itself. So this is just a very useful thing to remember. If you want a very explicit example, if you take the permutation 1, 3, 2, 5, then if you work this out, it should be 1, 5, 1, 2, 1, 3. And again, if you check this out, 1 goes to 3, 3 goes to 1, but 1 goes to 2, 2 goes to 1, but 1 goes to 5, and then finally 5 goes to 1. So it checks out. Now, this isn't the only way. I mean, you can always, this is one way to write a cycle as a product of transpositions. The reason it's not the only way is because, for example, you could always stick in some silly things. For instance, you could write 1, 3, 2, 5 as 1, 5, 1, 5, 1, 5, 1, 2, 1, 3. And of course, if you do 1, 5 3 times, you flip 1 and 5, then you flip 1 and 5 back, then you flip 1 and 5 back. It's the same as 1, 5. So another way to think about it is the product of these two permutations is the identity. And so they cancel out. And so you can certainly always stick a bunch of duplicates into your product of transpositions and get another product of transpositions which has the same, which gives the same permutation. So the number of permutations, the number of transpositions isn't, at least at first glance, something that you can pin down. There's always lots of ways to do it. The other remark I was going to make is that, as I said, one way to interpret this is that you can always sort a list by repeatedly exchanging two elements. And just to illustrate that, what I'm going to do is start with the list 1, 3, 5, 2, 4, and suppose I want to put that in order. So on the right-hand side, I'm going to write down the permutations that I'm going to do. So first, I'm going to switch the numbers in the third and fourth positions. That's how you read that. So that means I'm going to switch the 5 and the 2, and it becomes 2, 5. My goal here is to move the 2 all the way to the left. So having switched the third and fourth positions, now the 2 is in the third position, and I switch it with the 3, which is in the second position. That's the transposition 2, 3. Now I've moved 2 into the second position, but I've still got 5 and 4 in the wrong places, and they're in positions 4 and 5. So I put this permutation in, and it flips them back. And so the permutation 3, 4, 2, 3, 4, 5, or 4, 5, 2, 3, 3, 4, depending on how you read it, will take this, this list and sort it into order. And if you've ever done any programming, you may have come across an algorithm known as bubble sort. And in bubble sort, what you're doing is you're always going through your list over and over again and switching things that are out of order. And eventually you'll put the list into sorted order. And in fact, lots of sorting algorithms use transpositions. And so this fact that any permutation is a product of transpositions is kind of the same thing as saying as you can always put a list into order by only using the interchange of two elements at a time. Great. Now, as I mentioned, our goal is to introduce this idea of even and odd permutations. And I'm going to skip ahead a little bit just to look at the main theorem. So the main theorem says the following thing. Suppose you take a permutation in the symmetric group on n elements, and you write it as a product of transpositions. Now we know that there's lots of different ways to do this, but what turns out to be the case is either when you do this, you always get an even number of transpositions, or you always get an odd number of transpositions. So the theorem says every expression of sigma as a product of transpositions, there's two cases. Either every expression of sigma as a product of transpositions has an even number in it, or it has an odd number in it. And so we can divide up our permutations into two classes. the even ones, which can be written as a product of an even number of transpositions, and the odd ones, which can be written as an odd number of transpositions, product of an odd number. So transpositions themselves are clearly odd because they can be written as a product of just one transposition, namely themselves. 3 cycles, A, B, C, so just 2 examples here. The permutation AB is odd because it's one transposition. And the permutation ABC, if we use our trick for writing permutations, cycles as products of transpositions, this is ACAB. It's even because it's a product of 2 transpositions. And what we need to show in order for this to make sense is that no matter how you write your permutation as a product of transpositions, you may get different numbers of transpositions in that expression, but you're either always going to get an even number or you're always going to get an odd number. So to prove this, we're going to start with a special case. We're going to look at the identity element. And we're going to suppose that the identity element is written as a product of transpositions. And we're going to show that no matter how you do that, you always have to use an even number of transpositions. Now, as we said, the simplest way to write the identity element as a product of transpositions is 0 transpositions. And 0 is even. So that's okay. And by way of another example, you can also write the identity element as, say, 1 transposition, like 1, 5, times itself. And that's a valid equation, but again, the number of transpositions which occurs in that expression is 2, which is even. So that's consistent with the theorem that we're trying to prove. So this result takes a little bit of work, and the proof is going to be by induction. And the idea is the following. We're going to suppose, well, first of all, we know that if R, which is the number of transpositions, if E is, then there are no, maybe I'll write it this way. R equals 1 can't occur. Because that would mean that E was just equal to tau 1. But if tau 1 is a transposition, it's not equal to the identity. So the identity is not equal to any transposition. So if you have an expression of E as a product of transpositions, it's got to have more than one transposition in it. Certainly we can write E as a product of 2 transpositions, but we're going to assume, so for our inductive hypothesis, we're going to assume that if E is a product of fewer than n transpositions, let's say R, so R is less than n, then R is even. So we have a number, and we know that if you look at any, so we write E as a product of n transpositions, and we know that any shorter expression only involves an even number of transpositions. And now what we're going to try to do is to sort of reduce the length of this, more or less. And so if we show we're going to reduce the length by an even number, and so, well, you'll see how this goes. It's probably easier just to work it out. So the way we're going to do this is we're going to focus our attention at the end of this product of transpositions. So we're going to look at tau n minus 1 and tau n. And let's start with tau n. It's a permutation of the form AB, where A and B are different. And pick one of those. Let's focus on A. So tau n minus 1, there are 3 possibilities for it. Namely, it could not involve A at all, but it could include B. It could involve A but not B. It could involve A and B, or it could involve neither A nor B. So what are the possibilities? So tau n minus 1 has 4 possibilities. Namely, tau n minus 1 is CD. This is the first possibility, where C and D are different from A and B. Or tau n minus 1 could have an A in it, but not a B. Or it could have a B in it, but not an A. Or it could have both A and B in it. Now, let's look at these cases in turn. So in the first case, let's look at case 4. So in that case, tau n minus 1 is AB, and tau n is AB. So E is tau 1, blah, 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 up to tau n minus 2, and then it has 2 ABs at the end. But AB times AB is the identity. Because, B goes to A, and then goes back to B, and A goes to B, and then back to A. And so that means that we can take these, they don't do anything, and so if we just, this should be a tau n minus 2. This implies that tau 1 up to tau n minus 2 also has to equal the identity. Because it's the identity times AB is the identity. By induction, now we've written E as a product of fewer transpositions. So by induction, n minus 2 is even. And so n is even. Because if n minus 2 is even and you add 2 to an even number, it's still even. So that's the first case. Now, things get a little bit more interesting. In the second case, well, let's look at case 1 next. In that case, we have CD, AB. This is tau n minus 1, and this is tau n. And that's equal to AB, CD, because the product of disjoint cycles commute with each other. We proved that. And a transposition is just a cycle of length 1. So the reason we want to do this is you'll notice that we've moved the A, which was at the very end of the expression, back 1 step. So now, if in case 1, we've arranged for A to move back 1 step in this. Originally, A was in tau n, but now it's in tau n minus 1, and it's not in tau n. If we look at case 2, we have AC, AB is at the end. Well, let's work that out. A goes to B, B goes to A goes to C, C goes to A. This 3-cycle is the same as the 3-cycle BCA, because both of them do exactly the same thing. A goes to B, B goes to C, C goes to A, B goes to C, C goes to A goes to B. And by our trick for rewriting this as transpositions, this is the same as BA, BC. And again, you'll notice we've moved A, which used to be occurring in the last tau n, is now in tau n minus 1, but not in tau n. So A occurs in tau n minus 1, but not tau n. And similarly here, A occurs in tau n minus 1, but not tau n. And we have one more case, which is the case BC, AB. Again, we write that out. It's A goes to B goes to C, and then C goes to B and B goes to A, we do the same thing. We cycle it by 1, and then we rewrite it as a product of transpositions, and we get CA, CB. And again, we have A in tau n minus 1, but not tau n. So what have we done? We took our expression for E, which was tau 1, tau n minus 1, tau n, and we moved A one step to the left. Now we look at tau n minus 2, tau n minus 1, and we now there's two. I should mention, the other possibility is that the very first case we looked at, case 4, we didn't move A one step to the left, but we shortened the expression because we canceled off the ABs. So there's two possibilities here. Either tau n minus 2 is the same as tau n minus 1 and they go away, or we're in the other cases and we can move A yet another step to the left without having it occur in to the right of that point. So we repeat this. They either cancel, in which case we're done, because n minus 2 is even, so n is even, or we move A to the left one step. That is to say, A occurs in tau n minus 2, but not tau n minus 1 or tau n. And we keep doing this. And one of two things happens. Either somewhere along the line we get that case where two things cancel. Either there's a cancellation, so the expression, so that by induction n is even. That's the case where two adjacent transpositions become the same. They drop out. The list that's left gets shorter. By induction, it's even. So when we put the two things back, it's still even. Or we get 1A appears in tau 1, but not tau 2 out to tau n. But that's a problem, because if that happens, our permutation, our E, moves A. Because if you have E is equal to tau 1 out to tau n, and this is of the form AX, let's say, and there's no A's out here, then when you work this out, all of these ones here leave A alone, and then A goes to X. So therefore, this permutation, which is supposed to be the identity element, moves A somewhere, to X maybe. But it's the identity. That can't happen. Because the identity doesn't move anything. So that case can't occur. So what that means is as you move the 1 down the way, or the A down the way, at some point you have to get a cancellation and the length has to get shorter. You don't know where that's going to be, but wherever it occurs, the length gets shorter, and so therefore you conclude that a cancellation happens somewhere, and so you get that you get the identity is a product of n minus 2 transpositions, which means that n minus 2 is even by induction, and that tells you that n is even. So this is a really nice kind of reduction argument to show that if you have the identity element as a product of transpositions, there have to be an even number of transpositions involved. And now we can use that to prove our final result, the main theorem, because suppose sigma is an arbitrary permutation, and you write it as, let's say, tau 1 up to tau m, where the tau I are permutations, are transpositions. And you also write sigma as, let's call them alpha 1 up to alpha k, where the alpha I are transpositions. And what we need to show is that either m and k are both even, or m and k are both odd. And to do that, we write sigma inverse sigma is alpha 1 up to alpha k inverse times tau 1 out to tau m. But here's a nice little trick. Remember that, first of all, if you take let's call them alpha 1 up to alpha k inverse, when you take the inverse of a product, you get the inverse of the elements, but in the opposite order. That's the first thing. And the second thing is that the inverse of a transposition is itself, right? Because if alpha is a transposition, if it's xy, then alpha squared is xy, xy, and this is the identity element because y goes to x, but then x goes to y, so y goes to itself, and x goes to y, but then y goes to x, so x goes to itself. So this is, since the product of permutations is a permutation, since the inverse of a transposition is a transposition, this is just alpha k dot 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 down to alpha 1. And that means that sigma inverse sigma, which is the identity, is alpha k minus 1, alpha 1, tau 1, up to tau m. And by the proposition that we proved a little while ago, this has k plus m element transpositions in it, so k plus m is even. And if the sum of two integers is even, that means that either k and m are both odd or both even. And that's what we were trying to prove. Just to give a few examples here, if you look at cycles, like the cycle 1, 3, 2, we know that this is 1, 2, 1, 3, so it's even. But if you look at the cycle 1, 2, 3, 4, which is 1, 4, 1, 3, 1, 2, it's odd. So a little lemma would be that a cycle is even if and only if its length is odd. 3 cycles, 5 cycles, 7 cycles, 9 cycles are even permutations. It's a little strange, but that's the way it goes. And 4 cycles, 6 cycles, 8 cycles, and so forth are odd. And you can read off, if you have the cycle decomposition of a permutation, you can tell whether it's even or odd by using this fact. So, for instance, if you look at the permutation 1, 2, 3, 5, 6, 1, let's say 7, 8, 9, 10. This is a 3 cycle, so it is even. This is a transposition, so it's odd. And this is a 4 cycle, so it's odd. So the total permutation is odd plus odd, which is even, plus even. This is even. And the reason for that is you can write this as a product of even number of transpositions. This is just one transposition, and this is a product of an odd number of transpositions. So altogether, you'd have an odd number of transpositions here, an odd number of transpositions here. Put them together, you get an even number of transpositions. and then you include that with this, and you still have an even number of transpositions. And in fact, you can check the little proposition that the product of even permutations is even. And then, as you would expect, even times odd is odd, and odd times odd yields an even permutation. So that's maybe helps explain where the name comes from, even and odd. And finally, because the product of even permutations is even, the collection of even permutations forms a subgroup of Sn. So let's prove that a little bit more carefully. So we let An, it's called the alternating group, be the collection of permutations in sigma n, in Sn, the symmetric group, such that sigma is even. And the claim is that An is a subgroup. And remember how we check that. We imagine that we have sigma and tau, two elements of this subset. And we need to check that sigma tau inverse is also an element of An. In other words, that sigma tau inverse is still even. And the proof of that is we write sigma as a product of transpositions. And because sigma is even, it's a product of an even number of transpositions. And we write tau as a product of transpositions. And because it's even, it's also a product of transpositions, of an even number of transpositions. And then sigma tau inverse is alpha 1 out to alpha m, beta 1 out to beta r inverse. And by the same argument that we used earlier, the inverse of this product of transpositions is just the transpositions in the opposite order. And so the length of this expression is m plus r. And so m plus r is even, because m and r are both even. So sigma tau inverse is even. And so sigma tau inverse belongs to An. And so An is a subgroup. And the other part of the claim about An is that it has half as many elements as the symmetric group. And to see that the number of elements in An is n factorial over 2, what we do is we pick any transposition. So let's pick the transposition 1, 2. And now if sigma is in An, sigma times 1, 2 is odd. So it's not in An. And I want to set up, so I'm going to take, if you want, I'm going to take the set of odd permutations. Let's let B be the set of sigma in Sn so that sigma is odd. And we know that An together with B is all of Sn, and that An and B have have nothing in common. So we just have to check that they have the same number of elements, and for that I have a function, let's call it lambda, is a function from An to B, which sends a permutation to that permutation times 1, 2. And this map is bijective because it has an inverse. Lambda inverse of tau is tau also times 1, 2. Because if you first do lambda and then do lambda inverse of sigma, that's sigma times 1, 2 times 1, 2, which is sigma. And similarly, lambda inverse of tau is first you take tau, multiply it by 1, 2, and then you multiply it by 1, 2 again, so you get back to tau. So if you have a function which has an inverse function, then it must be a bijection. And if you have a bijection between two sets, they must have the same number of elements. So since lambda is a bijection, it has an inverse, so it must be bijective. We know that the number of elements in AN is equal to the number of elements in B, but it's also the case that the number of elements in AN plus the number of elements in B equals n factorial, and so they each have n factorial over 2 elements. And let's look at the first kind of what is the group A4? So what are the even permutations? We know that there have to be 12 of them because 4 factorial is 24, so 4 factorial over 2 is 12. And so the identity is even. The 3 cycles are even. And how many 3 cycles are there? Well, there's 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4. So basically, to make a 3 cycle, you have to pick 3 elements from your set of 4, which means you have to leave 1 element out. So there are 4 possibilities, but there's actually, each of these 3 cycles gives you, there's a pair of them because you can put them in different orders. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 elements. And so we're missing 3. And the ones that we're missing are the products of 2 cycles, products of transpositions. So there are, in the group A4, there's the identity element. There are 8 3 cycles, and there are 3 products of 2 transpositions. And those are all of the even permutations that you can make on 4 elements. Okay, so that's a lot of material, and let's stop there.